In this video, I'm going to be going over the homework assignment that was assigned on Friday, November 17th, 2017 for Honors Precalculus. I'm going to be going over this using the Desmos calculator, so if you want to follow along with your calculator, you can, but I think this will show up a little bit better here on this rather than trying to look at my calculator screen. All the problems are from section 2.1, so if you want to follow along, please do so in the book. I'm just going to show you how we go about doing the work. So, for number 53, we're comparing the year to the hourly wage. And notice that it says that we don't type in the year, instead we say number of years since 1970. So here in my data table it says 5, 15, 25 instead of 1975, 1985, 1995. And so this is how we enter in our data. And then it asks for us to find a linear regression. And so we have this equation right here, 0.54x plus 4.07. Now it asks, what does the slope mean in this context? Well, x is years and y is the wage. And so what that means is that every year the wage goes up by 0.54 or 54 cents from 1970 to 2002. That's what that's telling us. Now letter B says use this model to predict the population worker average hourly rate in 2010. So that means we take this 0.54. Now instead of 2010 we plug in 40 because that's the number of years since 1970. And we add 4.07. and we get 25.67. And so that is our estimate for letter B for number 53. All right, let's move on to 54. Now for 54, we're talking about all the rectangles whose perimeters are 100. And so with all the modeling problems that we did, I always said the same thing. Plug in numbers first. What would be the area if one side is 1? If one side is 2, if one side is 3, and so on. And so if you work your way up to it, if one side is x, then the other side is 50 minus x. And when you multiply them, that's the area formula you get. And so here's the graph that I see. Well, I don't see a whole lot. So I'm going to make my x max 100. There we go. So it goes up and then it comes down. But I need to make my y max bigger. So make that 100 and make it 1,000. There we go. Now I see it. Now it asks, find the dimensions of the one with maximum area. Now anytime we talk about maximums or minimums, we have to graph it. There's no other way around it. So there's our maximum. Now the x value is one of the sides, 25. The y value is the area. So a lot of people make the mistake of saying the dimensions are 25 by 625. No. 25 is one dimension, 625 is not the other. So if 25 is the width, then the other side, the length, is also going to be 25. Because if this is 25, then we plug x in, 25 in for x here, this quantity right here, the length, that will also be 25. So that's the answer for 54, 25 feet by 25 feet. For 55, they ask us to plug in the revenue formula that they give us, and they said state the dimensions of a viewing window. Now this problem is really all about reading the problem. Because a lot of people will say, well, okay, well, it says I want to be able to see from 0 to 100,000 units. So a lot of people will say, well, just make your x max 100,000. And voila. Well, that's not reading the problem because x is in thousands. So if I want 100,000, then I need to take off 3 zeros. And let's fit that. So let's see, let's try 100,000. No, that's about right. So I go from 0 to 100 for x, and about a 0 to 1,000 on y. And that allows me to see this part of my graph. And this is all we have to do, is just state the viewing window. Now the second question asks, how many units should be produced if the total revenue is to be 1 million? So I type in y equals 1 million. Now if you type that in, again, you didn't read the problem, because it also says the revenue is in thousands. So that means I need to back this up, take away 3 zeros. Now if I zoom out, there we go. If I produce 107,333, because this is in thousands again, so I have to move that decimal point over 3 places. 107,335, that's how many units. But notice that this is a quadratic, which means it goes up, and then it also goes back down. So I could also produce 372,665, and that's another answer that will work. So to give you a sense of what this graph is shaped like, let me change my window. Here's what's really going on. And so we have 2 answers. These 2 answers are when our revenue will equal 1 million, because both our X and our Y are in thousands. Number 56. Number 56 says that a large painting is 3 feet longer than it is wide. The wooden frame is 12 inches wide, and the area of the picture and the frame together is 208, so find the dimensions of the painting. Now, we know that the painting itself is 3 feet longer than it is wide, but you have to add in the 12 inches. Now they're trying to mess you up here with this problem because it's 12 inches. Well, it's an extra foot on each side. So that means however long the painting is, you have to add a foot for each side for the frame. Same thing for the length, up and down. And so what we're asking for is, when is it equal to 208? So here's what I see, and I need to extend my window so I can see what's going on with y, so I'll make that 300. And there we go. That's where they intersect at 11. So when x is 11, that's when this will have a total area of 208, which means x is 11, that's one length of the rectangle, and then 14 will be the other dimension of that rectangle. So 11 by 14. Moving on to 57. We've got a rectangular patio that's 25 by 40, and it's surrounded by a border. But we don't know what that is, so that means that's x. So up here in our formula, we have 2x plus 25 and 2x plus 40. Now they tell us in 57, and this is a very subtle thing that the authors of the book did, they said the area of the strip, that is the strip around the rectangle, that's 504. So what I did is I also put this in, minus 25 times 40. What I'm doing is I'm subtracting away that middle part, because we don't care about that. The middle part's not there. It's just the outer bit that we care about. So we want to see, when does this whole thing, with the middle taken out, equal to 504. So I'll adjust my settings. And so I get an intersection of 3.5. So that is the value of x that makes this equation true, that of 3.5. All right, now on to 58 and 59. Now those are those problems that we talked about where we, similar to the one in class, where we increase price and or decrease price and increase the number we sell. And so x is the number of price increases. So our formula is 800. That's the number of currently rented units we have. And then every time we reduce the price, we get 20 more. So that's 800 plus 20x. Then we say the rent is 300 to start with, but we take off $5 every time we lower the price. So it's 300 minus 5x. And so that is the expression for the total amount that we take in. Now the question is, find a graph for rent levels between 175 and 300. That is x equals 0 to 25. So I'll set 0 for x min, 25 in for x max, and let's play around. Let's make it 100,000, 10,000, and so on. Oh, there we go. Let's take off that 0 and make this about 5. There we go. So what's our highest value here? There it is, $250,000. Now, Part C asks what rent will yield the maximum. Now, some people will look at this and say, well, $10. No, 10 represents the number of reductions. So that means we're reducing the rent 10 times. How much are we reducing it by? $5 each time. So we're taking off 5 times 10. And since we're starting at 300, that means 10 reductions will bring us down to $250 per month. That will be the amount of rent that maximizes this curve for us. Now the other one, here we talk about sales in soda pop machines. We sell 26,000 for 50 cents a piece. Now here's what we're doing. We're raising it by a nickel. And every time we raise it by 5 cents, we lose 1,000 cans sold. So this represents the total amount of money we take in. So Part B says we want to find a graph that gives us a maximum. So what we'll do is we'll extend the Y max. So we'll keep getting bigger and bigger. Up there it is. All right. So I can make that 20,000. All right. And so it asks, how much should they charge per can to realize the maximum revenue? What is the maximum revenue? Well, the Y value is our maximum revenue, $16,200. 8 represents the number of price increases. So we're going to add a nickel 8 times onto 50 cents. So if we add that nickel 8 times, we're going to be charging 90 cents a can. 90 cents a can will maximize this curve. For the next one, here we've got projectile motion. So they give us that it's launched from the upper deck, that's 85 feet above ground, with an initial velocity of 92 feet per second. So here is our position function. So it says find the maximum height of the baseball. So I'll hide the velocity graph because I don't need that right now. So it goes up, and I need to see it when it starts to come back down. So let's see, 10, 100, 1,000. There we go. So the maximum height of the ball is 215.25 feet. That is our vertex of this parabola. It goes up to that point, and then it comes back down. Part B says, how much time is it in the air? So we want to know when does it hit the ground. So we're looking at this point right here. And so that's at 6.54 seconds. That's from here, from time 0 to here is when it's in the air. So that's how far it is. Now, Part C asks, determine its vertical velocity when it hits the ground. Now I've got my formula, and I can plot it, but an easier way to do this would be to say, all right, well, I've got my value, so I plug in 6.54, and Desmos will just give me that number, which is negative 117.28, and that is in feet per second. So now, on to 62, we're still in feet. So this is our equation for position. We start with an initial velocity of 48 feet per second. That's what it's thrown up at. And it's thrown up from a height of 3.5 feet off the ground. So there's our equation. It asks, what's the maximum height that the ball will reach? And how many seconds will that take? So actually, we don't even need the velocity equation for this problem. So I'll X that out. And so I'll extend my window to there. And there we go. Now x is time. So it takes 1.5 seconds to reach its highest height of 39.5 feet. On to 63. Now in 63, here we're firing a firework 10 feet off the ground with an initial speed of 80 feet per second. So we graph our equation. So we've got our graph, and I'm just going to adjust my window so that I can see everything there. So there's the path of our projectile. So what is the maximum height above ground that the bomb will reach? So right here, it'll reach 110 feet. But actually, I made a little mistake, because actually this equation's wrong, because it's fired from a spot that's 10 feet below the Earth's surface. So actually that's not a plus 10, because that would be 10 feet in the air. It's actually minus 10, 10 feet below ground. So the highest that it reaches is 90 feet, and that's 2.5 seconds later. And then the final question is 67. I think I put 64, but that was my mistake. It should have been 67. So we want to graph this scatter plot. So let me zoom back. And so here is what our scatter plot looks like, and we've got a regression line. Now, it says to interpret the slope. Now, X is the age in months of female children, and Y is their weight. So what that's telling us is that from 19 months to 43 months, on average, these children put on 0.68 pounds every month. Now, letter E says, use this regression model to predict the weight of a 30-month-old girl. So I'll use this 0.68 times 30 plus 9.01, 254, and there we go. There is our prediction for the weight of a 30-month-old. If you have any questions, please email me, and I will email you right back. Thank you very much.